Hey everyone, in this video I'll be deriving the expression for the moment of inertia of a rigid rod as seen in the upper right. Now this rod can be assumed to be of uniform mass density and it's of length L. We'll call it of length capital L. Okay? It's uniform mass density, meaning that from length 0 to L, at any point, you can take whatever sized chunk and the average density of that chunk will be the same. So we can write that as lambda. That stands for mass density in physics. And that is, well, mass per unit length. Okay, that has some mass density, m over L or lambda. Okay, so we want to calculate this moment of inertia expression from the leftmost edge of this rigid rod. So I've written the axes like such. Okay, so the moment of inertia can be written like this in the general most case, right? Now again, this is r squared integral dm, meaning that we're taking effectively infinitesimal sized mass chunks that are comprising this rigid rod, and we're summing over the entire mass and over the entire length of this rod. Right? We are integrating across the entire length of all masses. So this is a continuous mass distribution, in other words. Okay? So we need to rewrite this integral r squared dm in a different way, right? We can't just integrate straight away from here. So I'm going to take that lambda, which is actually like so, and I'm going to rewrite it. Let's go in the upper right-hand corner. We can say that mass is equal to lambda L. Okay. Actually, let me write L in terms of x in this case. I'll tell you what. Let me keep it L there, and when I write the differential mass, that can be written like lambda dl. Whoops. This is where I wanted to write x. I'm sorry. Lambda dx. So for every infinitesimal mass chunk we have, the mass of that is equal to lambda times that differential distance dx in that case. Okay, so we can take that dm and plug it in here so that we have integral r squared lambda dx now. Oh, and now, since we're integrating with our differential length x, we need to, instead of r, we need to have x in here. Okay. Remember, r is just a placeholder, a general variable for some distance. It can be x, it can be y, it can be z, it can be d. It's just a general distance. So I'm going to rewrite that as x. So rearranging, we have the lambda, mass density is constant, so integral x squared dx. Okay. Now we need some limits of integration. Well, in this case, we're integrating from the leftmost point of this rod to the rightmost. So that's 0 to capital L. Evaluating that integral is straightforward. We have x cubed over 3 evaluated from 0 to L. Plugging those limits in, we have this. And now we have lambda L cubed over 3. We're almost there. Now we can plug in what lambda is equal to. Remember, lambda up here is the mass density. So that is m per L. And this is the total length now, right? This is not x in this case. Lambda is the total mass divided by the total length times our L squared over 3. And we can rewrite that like such. One factor cancels out, and we have ml squared over 3. And this is our expression for the moment of inertia of a rigid rod.